So here we start our look at amines, and this is really our final functional group for this course. Now, the primary role of amines, as we've learned in many other reactions, is that amines can be both nucleophiles as well as weak bases. And when it comes to amines, we see, in terms of what affects their basicity, it's all of the same types of properties we've talked about previously. So ammonia, which has the conjugate acid of NH4+. NH4+ has a pKa of 10.5. If we add a methyl group to our nitrogen, that's an electron donating group. Electron donating groups increase basicity, which also means we decrease the acidity of our conjugate acid. Adding a second alkyl group to our nitrogen goes even further. But interestingly, adding a third alkyl group has a different effect. In fact, the third alkyl group in this case actually decreases basicity. And that seems like it's going against our pattern, but it turns out it's just a consequence of the fact that once we add that third alkyl group, the protonation step becomes too sterically hindered and decreases the basicity slightly. When it comes to aromatic amines are significantly less basic, or anilines. And that's not surprising to us either. We know that lone pair on the nitrogen on an aromatic ring is tied up in resonance, and because it's tied up in resonance, it's not functioning, very well as a base. So previously, we've learned a lot of different ways to make amines. Things like nitrile reduction, amide reduction, aniline reductions, and by that we mean nitro group reductions to form anilines. Are there other ways that we can make amines? Could we use an SN2 reaction? And it turns out SN2 isn't such a good way to do this. In fact, it works very well. In fact, so well that in many cases you'll get a tertiary amine or even a quaternary ammonium salt. And that's because even as you add one carbon group to your nitrogen, well, now you've put an electron donating group on a nucleophile, and so you've taken a good nucleophile and made it even better. So we need other methods to make amines. And one of the common methods is to use what's known as an azide. An azide, or N3-, can also function as a nucleophile. And so if you add sodium azide to a compound with a good leaving group, you get a very familiar at this point SN2 reaction. And then under a large variety of conditions, you can use LAH, You can use hydrogenation, or you can use a trialkyl phosphine. You can convert that azide into a primary amine. Another way to make amines, another new way, is known as the Gabriel amine synthesis. And again, this is another reaction that it sounds new, it's going to look new, but it turns out it's all a bunch of mechanistic steps we already know. So we take this compound, this NH proton here is highly acidic because it's next to two carbonyls. And so if you add base such as hydroxide to it, you can easily remove that hydrogen. If you then add this to an alkyl halide, we get yet another SN2 reaction. And so now we've placed an R group onto this nitrogen. From here, addition of an excess of sodium hydroxide. We could go through the entire mechanism here, but this is a reaction we already know. It's just an amide hydrolysis. First, we hydrolyze one of the carbonyl nitrogen bonds. Then in the next step, we hydrolyze the other. That's a reaction we learned in the acyl substitution chapter. But once we get two of those hydrolysis steps done, the reaction gives us the primary amine. We have a couple other ways to make amines. These other methods are a little more unusual, involve some more interesting steps. First, we have one of the most generally useful ones, which is known as reductive amination. Again, this is a reaction that consists of several steps that we already know, but we can start with an aldehyde or ketone, and we add to this some sort of amine. In addition to that, we add sodium cyanoborohydride, which behaves very, very similarly to sodium borohydride. It's a little bit different. Sometimes you can use sodium borohydride for this reaction, but more generally, that's the common reagent. The first step, though, is just the reaction of the amine and the ketone. Again, that's a reaction we've previously learned. That forms an imine. Second step involves sodium borohydride. And if you recall, that reduces carbon-oxygen double bonds. It can also reduce carbon-nitrogen double bonds. And in the exact same way that we've previously learned about that reagent, we get a reduction from the imine to the amine. So the reductive amination basically forms a new bond between the carbon of the carbonyl and the nitrogen of whatever amine we add. Our last two syntheses of amines are very different reactions because they both are processes that involve rearrangements. The first of those two is known as the Hofmann rearrangement. The Hofmann rearrangement starts with an amide and adds sodium hydroxide along with bromine and water. And in this reaction, we're literally going to take the carbonyl and remove it. So what we end up with is whatever this R group is over here. Here it's an aromatic ring. It could be something else. And the NH2 that's on the other side of the carbonyl will become directly attached to each other. So how does this work? So in the first step, hydroxide removes one of the hydrogens from the NH2 group in a step that looks very much like the formation of an enolate. It's not an enolate because this is a nitrogen here, but again, it's a very similar type of step. In the same way that an enolate can then do nucleophilic attack, if we have a good electrophile here, we can do the same type of thing, and so the nitrogen now picks up a bromine. Now, another equivalent of base comes in, removes the other hydrogen, again pushing electrons up onto oxygen. Giving us this intermediate, and this is sort of where the weird step takes place. Carbonyl reforms, but now instead of those pi electrons going and doing something else, the phenyl shifts over, grabs the nitrogen, and kicks out bromine. From here, this carbon is double bonded to two very electronegative elements. It's going to be a good electrophile. Hydroxide attacks. Oxygen adds its electrons back in. These pi electrons pick up a proton from water. And finally, base comes in, removes the hydrogen. We kick out carbon dioxide, and we pick up another proton from water to form our amine. So we've said all year that most of our reactions follow very distinct and very common mechanistic steps. Every once in a while we get something unusual that maybe doesn't follow one of those 13 basic mechanisms we've talked about, and this is a good example. For the next reaction, the same thing is largely true. And this next reaction is known as the Curtius rearrangement. In this reaction, we start with an acid chloride. We add sodium azide, which will do acyl substitution. And then it ends up very much like the Hofmann rearrangement, that whatever this R group is becomes bonded to the nitrogen, giving us, again, a primary amine. Now, you might expect there's going to be some similarities mechanistically, and there are. Again, first step is straightforward. Azide is a good nucleophile. It attacks the acid chloride. We've seen many acyl substitution reactions before, and this one's no different. Oxygen adds back in, kicks out the chlorine leaving group. And so that's our first piece. All right, what happens next? This is where the mechanism gets a little bit unusual. So one resonance form of the azide looks like this. And in this case, the negative charge adds in its lone pair. That causes this carbon our R group to shift over, and we kick out nitrogen gas. If you look carefully at the intermediate that we formed, this is the same intermediate we saw in the Hoffman rearrangement. And so through essentially the same sequence of steps, although here using water instead of hydroxide, we get the same basic process taking place. And then as before, we remove the proton, electrons shift over, we make carbon dioxide, and pick up a proton to again form our amine. So a few new ways to make amines. The last thing we're going to talk about in this chapter are reactions of amines. And in that case, there's not a lot to say here. And the reason is just in other chapters, we've already covered all of the important reactions of amines that we need. So we only have one left here. And that one new one is the Hoffman elimination. A Hoffman elimination involves typically a large leaving group. So if we take an amine, and this is the most common example, and we add a large excess of something like methyl iodide, we end up with an ammonium salt. Now, this is a very good leaving group. But it's also a very large leaving group. And so if we can combine the large leaving group with a large base, we could say something like T-butoxide. When that base is going to try and do an elimination, unlike in the Zaitsev elimination, which we learned about at the beginning of this course, because of the combination of large leaving group and large base, it's going to be much easier to remove the less substituted hydrogen. The mechanism is the same. It's still basically an E2 mechanism. It's just that because of the large leaving group, the large base, we get a steric hindrance, and the base goes after the most accessible hydrogen as opposed to forming the most stable product. So in a Hoffman elimination, and that's really the only difference between that and other eliminations that we've learned, is that in a Hoffman elimination, we get the less substituted alkene.